Okay, so we'll go through our presentation on what we want to do with spheres in the long term. This is sort of the objective in the long term, to work with a worldwide set of researchers for spheres. Everybody kind of knows this already, and I said it many times before, but spheres, as a quick overview, consists of these microsatellites that we see in the picture, the red and blue. And the satellites fly inside the International Space Station. And that's really important. These are not full satellites. These are satellite buses that don't have one objective. They have many objectives, which is to test metrology, control, autonomy, and artificial intelligence algorithms. Ideally, this is for anything that has distributed satellite systems, DSS, or in other words, when more than one satellite is working together. Although in some cases we'll find that we can use them to test when only one satellite is doing something. Initially, they were designed mostly for rendezvous and autonomous formation flight, and we're doing a lot of new things with them today, right now, that we'll talk about. The really big thing about spheres is that we are in a representative environment as far as software is concerned. So if we are validating software and we think about technology readiness levels, spheres can take you into a representative environment of 6 degrees of freedom, long duration microgravity, where software can be validated to up to TRL 6 or 7, depending on how much effort you put into it. Our key phrase for spheres has always been, if you can bring the space environment to the laboratory, take the laboratory into space. And this last part is really important, because what spheres is about being able to take risks, just as you do in the laboratory. The satellites have been designed so that no matter what you program to do with them, they can crash into the walls, they can fly around, they will not hurt anyone. The forces they eject are lower than the kick load of an astronaut. In other words, if these satellites were to fly around and collide with a wall, it'd be less force than when the astronaut pushes themselves off from the wall. So, and because they're inside space station, we can resupply consumables. That's both batteries and tanks, and the human can help do all that, and the human can also save them. So we really have a laboratory environment, not a one-time everything has to work environment when we're using spheres. Because we're talking about research, I left this slide in, although I will talk about it kind of quickly. In research, we want spheres to be able to help you do all of these things. Demonstrate and validate software algorithms. Not necessarily the exact pieces of code, letter by letter code, but yes, the high level algorithm that you are trying to use on hopefully a future mission. You want to be able to demonstrate repeatability and reliability of a system, so that you show that there's similar results as we go around. You want to be able to use spheres in order to determine the simulation accuracy. In other words, if you had a simulation of spheres doing something different than what you normally designed for, and you test it in space station, you have to be able to validate that simulation. We want to figure out the limitations for performance. Now, this is not just of the testbed itself of spheres, but really of the algorithms. When does the algorithm run into a problem? And hopefully you can find that independent of spheres itself. In a similar related note, you need to know what are the drivers that will matter the most. So given that you have some limitations, if you change something or other, what's the most important thing? And lastly, ideally, we can identify new physical phenomena. We might be able to see something that we hadn't thought about. In other words, by doing an actual physical test, we might discover the unknown unknowns in a very safe environment. Okay, so why are we here today? Now that we introduced spheres again, the main research version of it, not our general overview, but with some research ideas. Well, today, if a European researcher wants to use spheres, you need to find a USA partner who has funding for similar research or is willing to do it for free, and that's kind of hard these days, and has access to spheres through their NASA or CASIS agreements. MIT today, we're always willing to partner, but up to our available resources. We ourselves are limited to what we can do in space station, to whatever NASA or CASIS has approved as research. So we cannot just do any research that anybody wants and say, hey, MIT, let's try this. No, we have to go through NASA and CASIS and approve it so that we can get astronaut time for it. The MIT Space Systems Lab, our lab, we can take about 6 to 8 projects at a time and not really more. Well, our funding limitations, our personnel limitations cannot prevent us from going too much harder than that. And we're currently at about 6-7 projects with some fluctuation of finishing some, starting new ones. So we're kind of at our limit. So while we would like to do everything that has to do with spheres, we would rather have some people just do your own research. That's how we try to design spheres to work so that you can do your own research. You don't have to be doing everything. And yes.
Sorry, you are listing that require access to the spheres, but you do not mention the access to the ISS itself.
So
because this could also go to ESA for Europeans, or
well, that's what we're trying to do today. So today, ESA cannot grant European researchers access to spheres aboard ISS. We are trying to determine today, should ESA spend the resources necessary so that European researchers can come to ESA and say, we'd like to use spheres aboard space station. For ESA to be able to do that, ESA is going to have to go and find, especially crew time, find astronauts on our space station to do this. So the goal of today, the objective of today, is to say, should ESA invest the necessary time to train European astronauts to use spheres and to enter a partnership with NASA, specifically NASA Ames Research Center, which runs spheres at our space station, so that European universities who do not have to work with MIT can go and ask permission to ESA to use spheres. Okay, so moving on. This is the main hardware overview in slide 5. We have the sphere satellite. We have our communication box. In this slide, the laptop is provided by space station, but the communication box that's attached to it is a custom communication channel. When we're in space station, our satellites talk straight to the laptop and they don't talk with anything else. Today, the data stays there until manual processes take place and that data comes down to the ground.
Is there any plans, long-term plans, short-term plans for
slide 30-ish?
Okay.
Yes. So we'll talk about that in a second.
Okay.
The beacons is our metrology system. In other words, how we determine where we are. Spheres today pretty much always works with an absolute knowledge of where it is with respect to space station. We mount the beacons in non-location space station, and an ultrasound signal is measured to triangulate the distance between the known beacon locations and the floating spheres. That's where they know where they are. And then we have the two consumables I mentioned, the CO2 tanks and the battery packs. So moving on next. This slide I'm going to leave mostly for people to review later when you have access to the slides. Really the big thing is the control panel is super simple because it's all about autonomous control or remote control. You don't control the satellite themselves, you program them to do something. Other than that, you can see the main systems, the thrusters, the pressure gauge, where batteries goes, about 20 centimeters in diameter and 4 kilograms of total mass. So one thing I did want to talk about a little bit more than in other presentations is about how we do research with spheres. So in this slide, what we're seeing is that we start everything in the green color in simulation. In the green square, the scientists can write MATLAB code and C code, and then on their own time, however they see, they do a simulation, they look at the data, they analyze the data as much as they want, and then they modify the algorithm and keep going. The color coding in this box is what I call science time in green and overhead time in pink. So you really want to maximize your green time and minimize your pink time. That way you know that you're doing a lot of science with little overhead. That analysis is an important one because a lot of people think, oh, just analyze data super quickly. Actually, not really. As a scientist, you want enough time to analyze the data so that you can think of the new way to react to that data. So that's actually really important. A lot of tests, especially with the space shuttle in the old days, you only had a couple days to think about it and then you had to finish. With spheres, you could take several months to analyze the data before you need to have something new to test. Then there's the ground testing. The 2D ground testing in the orange beige square, that happens either at the MIT Space Systems Lab, and it could also happen at NASA Ames. They have a setup now to do that too. And when you're doing ground testing, it's a little bit of a larger cycle. You can do tests up to 20 minutes. When you send code for integration to MIT or NASA, it'll be a few days before they can actually run your test. Getting the data back to you will take a couple hours, but you could see that over 2 weeks or so, you could be running hardware tests in the ground. Once everything has been tested in simulation and validated in 2D ground tests, it gets sent to space station. The path usually is MIT to Ames to Marshall Space Flight Center, where they have the upload capabilities to send to space station.
What is ASC?
Ames Research Center.
Okay.
NASA Ames Research Center. So when the data gets to space station, this is important. We usually get about total of 4 hours of crew time. 2 of that is used for setup and turn on and clean up and all this stuff around it. And we get about 2 hours of science time in that. And during that science time, what we're doing is we're loading programs into the satellite, and every program can run multiple tests. So we're running test after test after test. During all that time, again, the data is in the laptop. It's not down to the ground yet. It goes to the server, and then a couple days later, usually it's actually within 1 or 2 days, but we get to 3 days to be safe. And about 1 week, we get the video.
From my understanding, how many tests can be run on average in this 2 hours of science?
In 2 hours of science, we can usually run about 12 to 20 tests, depending on the complexity.
That would be from how many researchers, or is it just
usually it will involve about 3 researchers or so in the science perspective. In that, in one test session, we might combine some docking and some formation flight. And we'll do about 5-6 tests of each. When we're doing basic tests, we've been able to do over 24 tests in a session. So we've been able to do 10 docking tests and 10 formation flight tests all in the same session.
Mm-hmm.
Some with 2 satellites, some with 3 satellites. When they're complicated tests, like the latest rounds that I'll go into in a second, in that case, we've been able to run about 12 tests. And they're all in a similar range of things, right? So it depends on the complexity.
I mean, there are all tests which have to be foreseen and prepared in advance. I mean, there is no possibility just to compensate for an error in that loop.
Correct. In this case, that's why we do take the time to validate things in the 2D ground hardware, because once you actually get a space station time, that's your crew time.
Mm-hmm.
And if you have a silly error, you're gonna have to go and tell the planners, oops, we had a silly error and we need a little bit more time. It doesn't make them happy, but many times they're willing to work with you to complete your science.
I mean, there's a lot of mistakes can be avoided, and this is
right. Exactly. So as long as the mistake is not something that demonstrates that you're just not caring, you cared, you did everything you could to try to avoid the mistake, it still happened, they usually work with you to finish your science. Okay. So just a quick more detail on how the test session goes when we're actually on a workspace station. We can have audio and video go to pretty much on all locations. In this case, MIT, Ames, and Marshall, they all see audio and video. And multiple other locations could be set up to have audio and video too beyond MIT. It's just a few months of paperwork to get everybody authorized and tested. Video is especially tricky because video requires I2 connectivity in Internet 2, which is a multicast connectivity, so not everybody has that. But audio is could go to many. Audio requires a lot of paperwork. Video requires I2 connectivity. So it's a challenge, but it can be done. And again, MIT is always willing to host people. And that's always Ames. If we do come agreement, Ames is willing to host them.
Is it real-time audio and video?
Yes, it is real-time audio and video.
And the video comes from the standard module VGA cameras. It's not a special camera that's set up, it's the actual cameras that
it's
are always
the standard cameras on space station. In GEM, it's a fixed camera that's always there. But we get two views. The second view from Node 2, they actually set up a camera for us to watch the experiment.
Okay.
It's one of their standard cameras, though. Okay. It's not a special camera.
It's a standard setup, it's not a... Okay.
Right, exactly. It's a standard camera set up in a special location for us, in the case of one of them.
Any plans for HD, or is it still SD?
We've actually recorded HD several times, and then with post-download, we do not currently have plans for HD real-time, because that requirement puts more constraints in when we can be scheduled to operate. So we'd rather
data bandwidth.
Exactly. We'd rather not have HD requirements and have more operational options than to have HD and less operational options.
Okay.
The standard operation is that MIT talks to Ames. Ames relays the message, or it sometimes filters the message depending on what the discussion is, and that goes to Paycom, Pod, and Marshall, and they talk to the astronaut. That is the standard way. Lately, MIT has been able to talk directly to the astronaut, depending on the payload complexity, and that has been very helpful, but we cannot count on that always being the case. It will always depend on both the crew member and the experiment being special in some sense or another. So again, the important thing was to realize who talks to whom in which ways as things are happening, and to point out that this is a slow process. We can run some of these tests within a couple minutes in the ground. It will still be 10 minutes in space station for the crew to set everything up, understand what they're doing, and move around. So that's why in 2 hours you can only do about 10 tests sometimes, because the crew will take time.
There is no data flow on this view graph.
Right.
What is the data?
Because during
upload a program, I mean from ground to from MIT to ISS.
2 days later.
Right.
3 days later.
Basically, there is no data flow here because the data going from the ground up to station happened already a few days before. We have to give Ames our code ready at least 1 week before, preferably 2 weeks before, and then it goes through all the channels to get up to station. And that already happened. So when I meant the slides about the test session overview, that already happened. And the data coming down, again, during the test session, it's all in the laptop. And after the test session, then it comes down 1 or 2 days later. Right? But there is no data flow in real time. Basically, that matters operationally. Okay, so now I'm going to talk about some serious upgrades.
Sorry.
Yes.
The majority of the communication between the astronaut and MIT or Ames is what then, about the status of the sphere, because there's no there's no possibility to intervene with the changing the test or anything.
Right.
That's
at the end of every test we have what we call a test result number, So when we get a test result number, it tells us at least what the satellite thinks it did. So if the satellite thinks it did okay or not, and combine that with the real-time video that we can see, and with sometimes astronaut feedback of what they experienced out there, we can make a good estimate on whether to continue or repeat a test.
Okay.
Right. So that's I guess the real-time data is only in the laptop, but the laptop will give some real-time feedback to the astronaut, although pretty limited.
We just sent the audio to ground. Who's deciding whether it's the test for successful has to be repeated?
So at the end of the test, we ask the astronaut to call down the number that he reads on the screen. Then the MIT team or the scientist team discusses that number and says good or not, and then they call up the number. So they ask Ames to relay through Marshall to the astronaut, good continue or bad repeat. So
it's a single number.
Usually, yes, it's a single number. It's a single 8-bit number from 0 to 255. Okay. Yeah. The Spheres of Bright section is kind of long. It's going to talk about several projects. We're going to talk about Vertigo, which is a vision-based navigation project. It's going to talk about RIMS, electromagnetic formation flight, about SLOSH, which is a fluid slosh experiment, and Interact, which is a human-machine telerobotic operations and interactions. We'll start with Vertigo and see how far we get right now. And so in slide 10, the Vertigo overview. Vertigo stands for Visual Estimation and Relative Tracking for Inspection of Generic Objects. Vertigo. The really big keywords is visual estimation and relative. The second keywords are generic objects, but really it's all about vision-based navigation, right? Can we use cameras to navigate around space station? Around other objects. It could be either space station or around another object. And actually the video we'll see is about another object. And we want to allow the scientists to concentrate on the vision-based system and not on the development of a satellite to test things or the communication scheme or other things like that. It's just you concentrate on vision-based navigation. So the goggles have 2 stereo cameras, and you can see them in the picture. Sorry?
Is one stereo camera or two cameras stereo?
2 cameras stereo, okay. And we actually have 2 of those setups aboard space station. But that should be correct. A pair of stereo cameras. We have a 1.2 gigahertz Linux CPU embedded in there. We have LEDs to illuminate things. We have Wi-Fi connection. We work with rechargeable batteries that are already aboard space station. And we added stickers. You can see that in the blue satellite. And those patterns are completely random. This is not a pattern recognition case, but it creates a better texture so that we can do more vision-based navigation, which means estimation and planning and mapping, rather than image processing, which means feature detection. So that's why the stickers are there for. And hopefully, as image processing gets better on the ground, which is really you don't need the 6DOF environment for, we can get rid of the stickers and do the visual tracking and image processing better. So on the next slide, just looking a little bit better at some of the pictures and what we're talking about. The really big thing that I wanted to point out is that the beige color and the red color are 2 different parts. They are not the same. They're not tied together permanently. You can remove the red part and the beige part. The beige part is the computer. That's the new computer. Is Linux based, very generic actually, that can remain attached to Spheres and give you substantially more processing power than Spheres has right now. And the red part is the actual cameras, the goggles in that sense. So as we'll see later with Slosh, we can use the computer for things other than vision-based navigation. Okay, so what I'd like to show next is the video from YouTube of our latest test session. And it's loading right now. And this video, which is sped up about 5 times real life, what it's showing is on the left image is what the cameras are capturing. As you can see, they are black and white cameras. You can see also very bright because we had the flash turned on, so we're pretty bright. On the right side, you are seeing the real-time image processing and navigation. What the system is trying to do is to maintain the green dot, which is the calculated geometric center in the middle of the image, while it's being provided as the satellite, the inspector satellite, is trying to do a circle around a satellite floating in station. So as you can see, we got it to work reasonably well. We are not done yet. That was supposed to be a circle planar with the deck of space station, and clearly it went at about a 45-degree inclination. So we're going to research why. That's why we're happy we right now have a few weeks to analyze our data and improve our research. Here you also saw going a little bit of board, but that is the current status on let's see, on spheres. You can see more videos on this other link, Space Station Lab videos. We have a lot of the videos. You'll see some of our very first trial at vision-based navigation, and those did not work. Our guesses for the inertia were wrong, so our gains were too high, and the size kept going unstable. As it began to do the circle, it always flew away of the system. So clearly we have more work to do, but fortunately this shows the researchy aspect of spheres and how we can try something until we get it right, as long as we're always learning something as spheres is being used correctly. Rings is another new payload going up to space station. This one is going to go up in June of this year. I believe in that's HTV4 or ATV4, one of the two. We have hardware on both ATV4 and HTV4. So
okay, good.
By the end of this summer, we will have rings there, and we will be operating in the fall. Rings is a very specific payload. It's about electromagnetic formation flight and wireless power transfer. So the idea is we can control the relative distance between the two satellites using only electromagnetic forces. We will be using the thrusters, but only for torque, and that is to simulate having a reaction wheel, which we did not have enough time to actually add to spheres. But the thrusters will not be used for translation. All the forces will be created through electromagnets, and the torques will be created through the thrusters. The combination of forces and torques between the two actually allows you to move in any direction, 6 degrees of freedom between the satellites. And the idea of electromagnetic formation flight is telescopes in the future that might be at L2 Lagrangian, Earth trailing Lagrangian, there's very few forces, or maintaining fractionated spacecraft at a course distance from each other, at least safe course distance. The next slide shows the rings hardware, and what I wanted to show there is if it's not clear that when we're using the rings hardware, we're not using the vertigo hardware. So in that sense, all these new pieces of hardware have been designed so that you can interchange them. There are only 3 spheres in space station. We will only have 3 spheres. So when we're using rings, we don't use vertigo. When we use vertigo, we don't use rings. We're actually thinking about an upgrade that will allow you to do multiple things, but rings itself is all by itself in this case. On the next slide,
what is the fan for?
The little fans, they're to cool down the wire. Actually, if you go to the next slide, I'll talk about the wire quickly. Each of the rings has 100 turns of an aluminum wire. because we could not use superconductor wires in space station because that requires cryogenics, and they don't like cryogenics flying around space station. So to cool down the non-superconductor wire, we use fans. We actually have an equal number of fans in with reverse spin directions, so that there's a net zero torque on the whole system. The magnets work at 83 hertz AC current, so that any DC currents, both because of Earth magnetic fields or any DC fields inside space station, should not affect us. At least that's the plan.
Synchronized.
They are synchronized. They use the infrared pulses that we use for metrology to also synchronize the electromagnets. Okay, so here we are again, continuing the presentation of spheres research and all the upgrades we're doing to spheres in the next year or two. Our first one, the next one that we're going to talk about after rings and vertigo is the SLOSH program. And the SLOSH program is the ability to collect long duration, as in several minutes at a time, fluid motion inside a tank in microgravity. Mainly because at this point in time, there are no models that have been validated with actual microgravity data of fluid slush in space. We're doing that because fluid slush costs a lot of money. It disrupts launch systems which use liquid fuels, either by creating undesired forces or by needing tanks that have a lot of baffles and other material in order to overcome a lot of fluid slush, and even then not completely. And we want to do this by using spheres and having the spheres move things around to create fluid slush disturbances. You can see that in this slide. Basically, we're attaching two spheres into a large frame. We're using the vertigo avionics that you see there. The blue boxes on these ends are actually the same avionics in vertigo, but instead of having the goggles in the front, we have the SLOSH avionics, which is basically a new IMU to connect a different range of IMU forces and torque that the sphere can do, and a connector so that we can connect the high definition cameras, in this case 5.1 megapixel color cameras that work over Ethernet, up to vertigo. So in this experiment, we see two things. Again, number one, we see the reuse of vertigo, and that's pretty important. And number two, we also see sort of the reuse of some of our ground systems. We're attaching the sphere satellites onto a saddle and a clamp that is basically identical to how we do that in the ground. Because in the ground, we don't care too much about alignment. We don't have a saddle. In this case, the saddle is built for the alignment. It's going to be a pretty large system. It's about 1.2 meters on total length. You can see here a sort of almost one-to-one scale between a human being and the system. And basically, that's the SLOSH program. Just as a quick technical information on the system. Like I said, 5.1 megapixels, 14.6 frames per second. The gyroscopes are going to measure up to plus minus 2G of slush maneuvers, while our current accelerometers are measuring 30 milli-Gs, which is basically the force created by the thrusters. So we can see that we can do all that, and at the same time minimize new components, because we are using all of the existing vertigo, so we're only adding this bottom part. SLOSH is expected to launch at the end of this year, in 2014. We should be operating the SLOSH system and collecting data. Okay, one of the largest programs that we are working on right now with spheres is called Medusa. It's the continuation of the original INSPIRE, which has funded vertigo and rings. And once again, it's to grow the capabilities of spheres through 4 launches. We have the universal docking port, which is seen right here. We call it universal because the same docking port can attach to each other. Identical copies attach to each other as long as they're facing straight into each other. So there's an alignment orientation on the roll in addition to the other alignments, but that allows them to be universal. These have been fully prototyped and tested at MIT for several years already, and that's why we hope that we can do this in a very short term. We hope to launch at the end of this year. We might have to pull some miracles. The integration process is usually much longer than 8 months, but we'll see if we can do that. The next thing that we'll launch in 2014 is the Halo multiport. We're calling Halo this blue and orange section in the image labeled number 1. Basically, you see that the spheres in the middle. The spheres are fully designed and built in Space Station. And we're currently designing this halo to surround the sphere to allow to dock multiple things onto the satellite so that it can do more complicated tasks than just a single UDP docking. The desired halo configuration will allow you to connect 4 elements plus vertigo all at the same time working on spheres. And the elements we want to connect are more universal docking ports, 2 robot arms. The robot arms are being designed by the Naval Research Laboratory in Washington, D.C. And they actually already prototyped, so we're going into the final redesign to be able to make them work with spheres correctly. And lastly, together with NRL, we will also design a manipulator hands to operate the system. More or less, the concept of operations of the Medusa project is that you start with the system searching for some targets. For example, in this case, it found this sphere right here. It starts with the arms pretty close together because they have a lot of inertia, so we have to maintain them as close as possible to the satellite, and even then our controllability, our control authority will go down as expected when there's a good amount of mass added into a system.
And the mass of the Halo plus the robotic arms is?
The mass of the Halo plus the robotic arms will be about 4 kilograms, which is about so basically we doubled the mass of spheres, which means we halved the linear control authority of spheres, and unfortunately more than half is actually about 1/4 rotational authority, because the inertia goes pretty high since the arms are on the outside. The outside of the mass makes a lot of inertia happen. It's also interesting to note here that what you're about to see could all happen autonomously in a much simpler way, but we're taking the hard route because the spheres is actually to test the hard things, not to do it the easiest way. So for example, we're going to go and grab the target satellite with an arm, even though we could have just asked the 2 satellites talk to each other. There's that actually would be pretty easy with all the research we've already done with spheres. But instead, the hard thing to do is to tell it, go and pick it up and make the other arm move and counteract the forces from the first arm.
And the target is immobile.
And the target might be immobile, or we might have it spinning. Actually, in the ultimate situation, would be a spinning target that you have to grab with an arm and capture it and learn about the dynamics. So, but we will do everything in steps, right? Spheres is a lot about steps, so little step at a time, we will be growing the complexity. This is our ultimate scenario. This is what we want to do by 2016. Now, there are several years and several PhD theses of research before we get here. But for example, in this case, we grab the target and we actually tug it. The servicer is a tug now, just pulling the other target until it finds the other part that needs to be assembled, and then it joins the 2 parts together. Once the 2 parts are together, then they're autonomous element, and we might have them fly around and control together each other, something like that, while the servicer becomes somewhat now it's trash, basically. It's done its job and saved the 2 big satellites. Even though it doesn't look like it, that's the idea. An interesting part of this is just by looking at the pictures, the CAD model, and we saw that the UDP is already designed and the arm is already designed. Halo is at the preliminary design stage. We have actually let's look at a trade requirements review. we've traded based on the requirements, the configuration, the structure, and is ready to go into a full preliminary design, but it's really on the very beginning. And as you can see also from the crude drawings, the hands are only in the plain conceptual stages. We know we want something, and DARPA is working with NRL, and MIT will join them at some point soon about figuring out exactly what it is that goes there, but it's not there yet. So that's up to 2016. The last addition to spheres that I wanted to talk about is the Interact project, which is human-machine interaction. And basically the idea is, how do we use spatial dialogues, including augmented reality and virtual representation tools, in order to research teleoperations of the spheres by using the sphere satellites. So teleoperations when the operator is operating a true 6 degree of freedom free-floating spacecraft under real conditions that include communications delays, simulated failures, but actual physical simulated failures, when we have different levels of autonomy based on Sheridan scales. So loss of autonomy in the vehicle, loss of control by the human, and so on. And we have the ability to also use multiple satellites being controlled by a single person, or multiple people controlling different satellites in the same team, but having to work together. Some of our metrics that we want to do are sort of those. I will provide a link to this video so we can download it later. You actually will not play here right now. We can play it later. And there's a second part to Interact, which is basically allowing real-time command and data handling from space. Basically, every block diagram here is what normal scientists have to worry about. We work with Boeing, who developed the Stella system, to hopefully be the first users of their system, which basically encapsulates all of the middle stuff that the space station has to do into what we call a TCP/IP tunnel. So as far as our Sphere server and the Sphere GUI is concerned, they're going to talk a direct connection of TCP/IP between the ground and the Earth, thanks to the Boeing system. And in the meantime, we'll be able to get the data that's going from the satellite to the Sphere's GUI all the way to the server in the ground, and have a Sphere's GUI do remote control operations. In the next slide, I want to point out some important parts. We do not have the bandwidth to do full video download from space station to the ground at this point. The ISS payload network does not have Wi-Fi, which means we do not have high bandwidth communications between the sphere and the laptop. And the payload LAN, the payload space to ground connections are also not that high speed. So we will not be able to do that. Both of the systems are expected to be upgraded in space station in the next year or so. In theory, by this summer. I'm going to say it's somewhere in 2014. Mainly because even if they do the hardware upgrade right now, I don't think they had the procedures yet for scientists to use those new hardware equipment. So somewhere in 2014, we're hoping we might be able to get full video from space all the way down to a ground system. In the meantime, we are researching remote teleoperations by using virtual worlds. When you only get telemetry from the ground, we can reproduce that system, that scenario in the ground, not to full detail, so it'll be just a cube with basically flat walls instead of the space station complexity. But since we know the Sphere satellites very well, and what we care about right now is inter-satellite performance, not intra-satellite, not spheres inside the space station, but just how the two satellites relate, we can do this all in the virtual world. So for example here, we can see when one satellite is as the estimator convergence is figuring out where it is, while the other one is going to its initial position, and the crew can visualize all that, and we'll be able to get some tools to say how are they moving. We're going to study where do you place markers on where you want to go, where you have been. If the satellites do some path planning and the astronaut needs to approve it, what's the interface for the crew to see the plan and then to say yes, go for it, or not, don't go for it. In the first stages of Interact, the crew will be commanding the satellites. Everything will happen inside space station. So hopefully the crew will be able to look just at the screen with the satellites nearby but out of view. So basically, yeah, kind of cover your eyes. Exactly. So we'll have to do some way to that they really stick around, only using the video, but see how they are able to control one or two satellites by their own, using only the virtual display. And then at the second part of this year, towards the end of the year, we hope to do that from the ground. That's the goal. So as a summary, we have vision-based navigation with Vertigo. We have electromagnetic information flight with rings. We're going to have slosh capture, so it's more about data analysis than experimentation, although we plan on doing some control. Can we overcome fluid slosh motion with control systems? And we have human-machine interaction and teleoperations. All of that, especially the first Vertigo rings and Interact joining into the Medusa huge project of robotic machine interaction in the next few years. So Vertigo, rings, slosh, and Interact are now. That's in the next year. And Medusa is a 3-year project.
Yeah.
So
very exciting.
Yeah.
And then you have some links as well to show.
Yeah, I think actually I made this other summary. If we have, I think we have some time right now. The question was asked a few times. So how does this happen? How do we get all this done? What if someone wanted to do other hardware? Because that's not enough. But someone wanted to do other hardware for space station, which could happen. I mean, there's interesting stuff to do. MIT is in a special place in that since we built spheres, we've been interacting with NASA and DoD, the DoD Space Test Projects and DARPA, for many years. So we've been able to create a relationship where we find the right proposals and we find proposals where NASA and DARPA will launch the hardware as part of the BAA, the ADC announcement. Sometimes we win them, sometimes we don't. But we look for those BAAs, and we've had good luck in some of the BAAs, like in the Rings and Vertigo one, to work with that. The other option that we're following, and this is going to be for a future project, in addition to fluid slosh, we're also researching fluid transfer, but that's in a very preliminary stage. But that one is an unsolicited proposal, so we applied to CASES. CASES is the entity that NASA created to manage unsolicited proposals to space station. So I don't know if there's an equivalent in ESA or if ESA accepts unsolicited proposals to get to space station. But overall, there is a lot of utilization in space station that NASA wants to make happen. Once you get the launch, and again, from MIT perspective, we're happy to discuss if you wanted to get some launch, can we create a solicited or solicited proposal to get some launches, or if not, that's why we're in this meeting to figure out if someone from Europe wanted to get new hardware to spheres, how do they get the launch? It's a good question. That's what we're researching here. So, but let's say that you get that, right? Let's say that you have a launch. Once you have a launch assigned, at least NASA assigns you a PIM, a Payload Integration Manager. There must be something equivalent in ESA.
There's PIMs, yeah.
There's PIMs. So the Payload Integration Manager will take you through the process of safety, testing, procedures, training, and software, which in our experience has been the process involved every time in getting hardware to space for us. Safety involves up to 4 safety meetings. An initial 0 meeting where you basically tell them, I want to do this, what should I worry about? And they give you feedback. Worry about this and this and this and this and this about space station. The idea of that meeting is there are thousands of pages of documentation of safety for a space station, but not every page applies to everybody. So that meeting is to tell a scientist what to worry about. Hopefully you already went and did some initial research and are going with something that you know is reasonably safe, but they'll tell you what else to worry about that you didn't think about, and they pretty much always tell you something you didn't think about. There's a preliminary design review meeting at the similar time when you're at the PDR level, where you go back to them and tell them, this is what I plan on building. Do you think it's going to meet everything you want? And then you go back and say, okay, here's my full prototype, my full design, this is what I want to build, I'm ready. And there's a third meeting, which is, this is what I built. So between 2 and 3, you better hope that you met everything, because you basically build it and they're just doing the final checking the boxes. Yeah, exactly. Sometimes you can combine safeties 0, 1, and 2 in different ways. Maybe just to have 0, combine 1 and 2. You combine 0, 1, and have a 2 separately. Vertigo had a 0, 1, 2 together. Rings, I believe, had a 0, 1, then a 2, then a 3. Because rings require large batteries, and they wanted to see our battery design evolve more between the initial time they met with us and the other times. And you pretty much always need an independent safety 3. I've never seen a 0, 1, 2, 3 all together. The safety 3 is pretty much necessary. It'll take at least about 8 months to go through a 0, 1, 2/3 process, because in 0, 1, 2 you're learning things and then you're going to the final check. So that I think the standard planning is at least 18 months to go through the whole process. So with MIT's and Aurora Flight Sciences experience, we've been able to shorten that to about a year in some cases, and we're dreaming about doing it in 8 months this time around with the UDP, but we'll see. We'll let you know the outcomes. Testing has to be done. There's basically always EMI, EMC testing that has to happen, unless you have absolutely 0 powered things. But spheres is powered, so if you're working with spheres, you have to do some EMC, EMI. You also have to go through off-gassing, and that's two things. First, before you actually build anything, they want to know every single material you're using in your experiment hardware, and then you send the hardware to NASA, and they'll actually bake it and put it into a special oven, literally, where they heat it up and measure what gases are coming out and tell you that if it's passed or not. Sometimes vibration is required. If they expect that your payload can cause any debris, they will require you to shake it. If not, it's up to you if you want to shake it in order to test for launch survival. For example, Vertigo did not require NASA shaking because there was basically nothing that could break and cause debris and go out just floating in space station. But we care a lot about the calibration of the lenses, so we actually tested Vertigo for Vive, and we basically realized that how important the calibration process was going to be, so we made it happen. And actually the first time we used Vertigo on station, we did do a calibration for the cameras. It went really well, and we were happy that we went through the whole process learning the system. You have to work on procedures. You will have to create procedures that modify the existing Spheres procedures for your specific payload. Vertigos took about 6 months to make. It wasn't trivial. It actually delayed operations a little bit. We launched in December, but could not operate until February until procedures were done. So lessons learned is procedures are really important, and they could delay something even more than getting a launch. So procedures are a really big deal. Training, on the other hand, can be a huge deal or a trivial deal. Vertigo, astronauts are trained on Vertigo. We go to Johnson Space Center, or in this case Ames, and actually Ames and MIT go to Johnson Space Center and train astronauts on the exact procedures and how Vertigo will be used. Many times actually going to the Building 9, the mock-up of space station, and doing it on a one-to-one real-life configuration thing. Rings, on the other hand, because the interface itself is purely mechanical, they don't really have to work with rings. They just have to start and stop tests. All they wanted to do was do a video, so we did crew training videos, and we sent them to the crew, and the crew might watch them before the launch. They might actually watch them until they're in space station.
This is a crew preference now that short videos are actually uplinked to the space station, just as a refresher reminder, either of a training session or the entire training. This
is the entire training right now for rings. So Vertigo, a little bit more complicated. The crew actually has to do a lot of interaction. That has a full training. Rings, no crew interaction, not much training. Slosh, my guess is there's not gonna have. It's gonna be like rings. Interact, the big robotic arms. Now, like they will have a big crew training procedure, crew training and procedure update. The other thing is software. Software is still very hard to upgrade if it has to work in NASA systems. A big reason that I pushed the Slosh team to use Vertigo avionics, and they accepted, is that Vertigo required an upgrade of the GUI that is used by astronauts, which meant reviews at multiple levels, both crew interface reviews and software running on a NASA laptop review. That's a 6 to 12 month process, and you cannot slow it down. Sorry, you cannot hurry it up. You cannot speed it up. You cannot shorten it. It's going to be that long. So, one big goal of any project with spheres should be that it doesn't need a GUI upgrade. And if it does, you have to plan for the extended process of that. The last part of the spheres talk is the programming spheres. And it's actually a very short introduction, mostly to give everybody a good example of what it actually means to program the sphere satellites, not only to see what they do. Because the hope is many people will become users of spheres, and not always with MIT doing the programming. Sometimes we want to do it, but other times you should do it yourselves. So that's the idea. The main thing about spheres is we have what we call the spheres core software. And the spheres core software creates a skeleton, a framework by which the real-time operating system works. And that's important. Spheres is a real-time operating system. It's not just a generic Windows or Unix, Mac OS based system. It actually guarantees time constraints as long as it's programmed correctly. And we've already preset several things that need to happen in a timely fashion, like control and estimation in this case. And we can actually make it happen at different priorities. There's also propulsion. We basically ensure that the thrusters are actuated at a granularity of 1 millisecond. So we can change the thrusters at 1 millisecond increments if needed. That doesn't mean they will open and close only 1 millisecond. That means that if you want it to be open for 27 or 28 milliseconds, we'll actually make that difference. There is a minimum opening time of 10 milliseconds, and there's no maximum opening time. So you could open in 10, 11, 12, and so on in 1 millisecond increments. If you notice, propulsion does not happen when estimation happens, and that's also important. The estimation, especially the one that uses the global control system, cannot happen when propulsion happens. So we are going to choose to do propulsion or estimation, but not both at the same time. There's communications. Communications happens at 5 Hertz based on data, the initial TDMA, a time domain multiple access protocol, that's initialized by the laptop computer. Whenever that starts, it starts a window of communications, and that can happen independently of all the other systems. So we have a periodic communications time frame, which is unsynchronized, is asynchronous to the rest of the system on the satellite. And what we see in the bottom picture, which we talk about priority, is we also allow a non-real-time task to happen. If the scientists need to run something that will take a long time and we're not sure where, or which has to be guaranteed to run after the controller happens, but which could take longer than you normally want it, you put it into a task. And that is an aperiodic and either synchronous or asynchronous task to everything that's happening with the real-time control. That's a lot of real-time operating system keywords, and again, that's what's important about spheres. Like in any control system, it's a full-blown real-time operating system that has been pre-configured for the scientists to do their things. Now, let me let's get some of that stuff. So, what do? We create an API that lets you very easily get data from the inertial sensors, including defining the sampling frequency, doing all the conversion from binary data to metric units. We have all the things that process the global sensors, including a lot of pre-processing in order to get rid of outliers, and an extended Kalman filter that actually gives you a state estimate that combines the inertial sensors and global sensors, unless you want to work on estimation. In the controller, we have a flexible control period, and we have a lot of functions to help you actually control things, which I'll show in a second. In communications, we have high and low priority traffic. The packets, again, it's a 5 Hertz TDMA, so it's reasonably low latency. Not fully real-time for some high-frequency systems, but spheres being a rigid body system, 5 Hertz is pretty much real-time. We have the ability for you guys to transfer large amounts of data or small amounts of data with very little effort. The propulsion, we have basic mixers, so that if you know your force and torque that you want to do, we will fire the thrusters to obtain those forces and torque. But you can also create your own modulation for the thrusters. You don't have to use the U1. And like I said, the GSP task, which is the flexible task that can be very long, very short, can happen in different, all throughout different events, and yet not interrupt any of the real-time systems that must happen. So, how does all this sort of look? It all starts in initialization processes. When we boot, we initialize some things that happen for the rest of the time the sphere has been reset. And when we start a test, we done some functions so when the test starts, so every time. And initialization is really important. Actually, that's one of the most common mistakes with spheres. People forget to initialize variables. Just because the satellite is on doesn't mean it's been initialized correctly, especially because we can start a test, stop it, then start again. Your variables are going to remember the old values and you initialize them again. That happens once, either once upon boot or once of the test init. The real thing that's happening through the whole system is the estimation process right here. We have the ability to get global data, that's the ultrasound measurements, inertial data, the IMUs, and then for to create either the task and the controller. This is the periodic, this is the aperiodic, as we said. From the hardware, you see basically all the data go into the estimation processes, but also interrupting the different things that need to happen. Usually it's the GSP control that sets the thruster times, although sometimes it might come from the GSP task, not very rarely. The user estimates are available to everybody. You could be calculating them yourself, or you could just be asking that they be given directly to control. Let's look at some of the examples. So what the big thing about the guest scientist program in Spheres is that it wants to let the scientists concentrate on their research that they're doing and not on other things. So we want to demonstrate a new rendezvous controller, a new controller for rendezvous operations. And we really don't care about the estimation communications, we just want it to happen. So we want to use the control interrupt for the guest scientist code, use the standard estimator, the standard communication spheres, and the standard position hold for the target satellite. So if you are writing the code for the chaser satellite, the one that's going to be working on, you're going to do nothing with the global data and with the inertial data. That's what they grayed out, basically because you're going to let the standard process run. So you're not going to grab the data and do a customized estimation. You're not going to do any fancy GSP task because your rendezvous controller is a basic control that fits into the real-time nature of things. So you put your code there, and when you're done, you're going to send the standard thruster times, and you're going to ask the standard estimate time, a state estimate, in order to determine what to control. Again, we don't touch any of the data or create any standard ones. The code would literally look something like this. It's actually quite close. You're going to call path state get with a variable that includes the chaser state, u. And that tells you where you are. 13 element state, 3 positions, 3 velocities, 4 quaternions, and 3 rotation rates. And it's basically accurate to within 20 hertz on a 20 hertz update rate if you initialize it correctly at the beginning. I'm skipping the initialization part of the code. But then in your controller that says running once a second, you figure out where you are once a second. Then you tell it to tell you where the other sphere is once a second. And that's going to tell you for sphere 2 at what time, where was it. So again, a 13 element state at a specific time. Then you're going to write your custom control function, which is going to return a control vector, which is basically 3 forces, XYZ forces, and 3 torque, XYZ torque. In order to be able to take the control, it likely needs to know where you are and where the target is. So I'm guessing that's how you would write your custom control in general. Then you use our standard mixer that already exists, control mix simple, which basically by being given, oh, apologies, that's supposed to be control, not forces. So by being given the control forces and torque, it's going to return the on times of the thrusters. We do this as a separate function because you could modify those right now if you wanted to. For example, to simulate a thruster that never turns on, you could tell it, no, except this thruster, don't do it. But in this case, we're not going to do anything with them and simply pass them on to the function to set the thruster times. And we're done. Sorry, one quick last thing with the control mix simple. We pass into it your state and your reference frame, just because it needs to know if the forces you ask for are in the inertial frame of space station or in the body frame that you asked for. So in this case, we call for it to be on the reference frame of the space station. So it needs to translate your actual state, that the body of the body of the satellite, into the inertial frame to match the forces that you want and determine which thrusters should open. But basically, the whole point is that if you are a scientist who wants to do control systems, you are worrying about one of these functions and everything else is already there for you, including all communications, including the mixer and the thruster interfaces. In the next example is just really the architecture. I'm not going to go into details of the programming. But basically, if you only want to demonstrate a new thruster diagnosis algorithm that potentially takes a long time to do because it's doing some estimates and some AI type of tasks, then you're going to put some of your scientist code in the task and maybe some in the controller to do some maneuvering and determine things, and modify it, like I said earlier, by simulating the thruster and the failures in the control interrupt before you actually tell the satellite to turn thrusters on and off. So in this case, the guest scientist code would go into GSP control and into the thruster on times and into the task where the task is basically calculating the error. The thruster on times is still standard, because in GSP control is where you actually told that don't fire these thrusters even though you were going to. So you're simulating in GSP control the failures, and in GSP tests where you're seeing if you can determine the failures. And again, everything else in GSP control is standard. We have already something that tells it to try to go somewhere, be it a position controller or even a velocity controller. So you can use our standard functions. So it's not trivial to use sphere score. I'm not saying that it's going to be done in 2 minutes, but it is reasonably simple to get started. A lot of the work has been done ahead of time. So you can concentrate on your work and not on using and learning spheres itself. So at this point where we will welcome any questions, obviously over email at this point. But I encourage you to go to these main sites. Under SS Elementary U spheres, the GSP, the Guest Scientist Program, actually includes a complete list of all the interfaces on how to control spheres, including all the complete API of controllers, mixers, the estimator, initialization routines, etc., etc. Under sphere/ISSDB, which is a hidden link, you will not find that linked anywhere else. You have to go to it directly. You will find the history of ISS operations of spheres, and it's a pretty long list. You'll find a blog of what happened in every test session if you go into the details of the test session, and potentially more importantly for the scientist, a report on what's happened on almost all test sessions except for the last few where we're still working on the reports. And on their spheres library.html, you will find our papers and theses that have been written about spheres. There's a lot of theses already and dozens and dozens of papers, so hopefully some of them are useful for you guys.